very much. See, can you see that? Oh, why can't I?
Yes.
I'm trying to make it full screen, but that is not really working. Oh, we'll have to do that without. But as long as you can see that, that's I think that's the important bit. Yeah, well, thank you very much. So my name is Arvid. I've been with the Paper Club for some time now. It has also been a while since I presented the last time, and so I decided to give a paper on. Oh no, did I? Okay, present this particular paper, which is actually part of a series. I hope I'm going to present in the next couple of weeks. These are 3 papers. They are all a bit older by now, but they are quite interesting, and I would call them golden papers because they are a bit aged, but they have aged well, I would argue. And the papers gonna be start with a very generic, very broad method, and then going more into more applicable algorithmic details as we go along. It actually looks, I mean, I don't know whether you have looked at the paper, but it probably looks a bit complicated at first, but actually it's the math is not fantastically difficult. And once, you know, with the first year of uni, you should be absolutely fine following it along. I also won't go into every detail of the paper, it's just a bit too long, but rather try to get to the gist of the methods. The book I actually mostly use to get to the stuff is this one. It's this fantastic book. Can highly recommend it. I put it in as a Christmas recommendation, but that just means it's been a while since I prepared this journal club. So yeah, let's get started. So what's the problem? As Peter alluded to, it's a problem about finding the marginal of a function. It could be a function of many variables. It's a very generic problem, right? So you can imagine many applications. For example, of course, probability theory, where you're often interested in, say, the marginal distribution. The idea is that the function itself has some structure to it, right? So rather than being a absolutely generic function, we say that the function itself is a product of subfunctions that, you know, contain maybe some subgroups of variables. Why do we think there's something there? Well, it's why is it difficult, right? So imagine we have a very generic function. If we want to calculate the margin, for any one of the variables, we have to sum over all the different combinations of variables that are there. And if there are many variables, they grow essentially exponentially, right? So if we have a binary system with a variable either being 0 or 1, we have 2 to the n different terms we have to sum essentially, which is expensive. But on the other hand, we can take the example: what happens if you have a function that is a product of functions, and each of those factors is essentially just a function of one of the variables, so that there's no overlap? Then, you know, the marginal becomes very simple, right? Because it's essentially just the function itself that contains that particular variable, and over the others we essentially just sum over. And so that is a lot faster to calculate and a lot cheaper. And now the question is there something in the middle that where we can exploit the structure essentially that we have of the factors to make our life as easy as possible? And can we find simple rules that are distributive? And distributive here means that we can sort of push the calculation across different entities and they talk to each other. But I hope it's going to be a bit more clearer further on what that actually means. What is the application? If you have read the paper, there's, I think, a lot what they talk about is codes. So in practice, you know, when computers talk to each other or messages are being sent, typically it's some form of binary signal of 0 and 1s. But in reality, there is never a perfect channel where the information comes through. There's always going to be some noise, right? So how noise could present itself, say it could be fluctuations in the currents that transmit the signal, and whatever is there to recognize the signal might misclassify it. Say a 0 might become a 1, a 1 might become a 0. And so what we generally get is a noisy version of the original signal. And if we were to take that as the message, we would often get just garbage. And if you imagine, like especially if a computer program, if you have a single wrong 0, 1 somewhere, it might potentially crash the whole system. So what people came up with is error correcting codes, essentially codes that contain additional bits that can be used then to sort of fix the message. And the very simplest example would be like a repeater code. Say you have a 0 and a 1, and you take, every time you want to code a 0, you take 3 zeros. Every time you have a 1, you take 3 ones. And if the message comes in, you hope that the noise levels are so low that of any block of 3 codes, whenever there is one of them changed, that is likely the noise change, rather than the noise having changed 2 bits at the same time. So when you get the message, and it might look like this here, you can do simple majority voting. Say the first 3 bits is 2 zeros, 1 1. So it's more likely to have been a 0 in the first place, so that would become our 0. The second bit 1 1 and 1 0. It's much more likely to be the 1 than the 0, and so we can recover the original message. Now this is working well. It's simple, works well. The problem is it's quite wasteful actually. When you can calculate how long a code should be in order to satisfy a Shannon's theorem. Essentially, what it says, the noisier a channel is, so the more likely a code flip happens. Not the more likely, but it's the noisier it is, desto longer essentially the codes have to be. Anything that is even longer than that, it's some form of waste. And so a lot of smart people came up with ways of coding constraints into these codes, like similar to the repeater codes, that allow them to quickly find what is the original code word. So one thing that's often used is parity bits, where essentially you have a bit that checks whether a sum of other bits should be 1 or 0, and that gives a constraint. And of course, the parity bit itself can also flip, but there are then other systems in place that sort of balance that out. If you have any questions at any point in time, please interrupt me and ask. I tend to go a bit fast at times. Yeah. So the question is now in practice. Say, imagine you get such a message, and you know there are certain constraints that should be holding true between the different parts of the message. What is actually the most likely message before the noise was added that came in? And this is, of course, a very, very important problem. If we had to do all our communications using the highest technical standards so that messages don't get corrupted, then any electronic communication would be just too expensive to use in practice. And so that's why these kind of error resistant codes are super practical in everything we do. We probably wouldn't be talking right now if it wouldn't be for them. In the paper, they give an example of a function, and that's going to be the prime example we're going to talk about. So the whole session of a structured function. So we have a function g of 5 variables, x1 to x5, and it consists of 5 factors. So factor a, yeah.
So in this method would be applied to the example you gave by trying to like decode parts of the message before decoding it, or like denoise parts of the message before denoising the entire message, or something along those lines.
It's you get on the one side you get a number of zeros and ones, and on the other side you have a function of probably less variables than that is your true message that was the intention of being permitted. The question is, given the message that comes in, what is the correct, aka the most likely message that was intended to be broadcast? And it can generally be described by such a function, by structured functions. Generally, the inputs are, for the time being, just 0 and 1. So imagine every variable we talk about is either 0 or 1. But it doesn't have to be, but it just simplifies things a little bit.
But where does the factor graph come in? Like where's the
For
factorization?
example, a parity bit would be a factor. So a parity
Ah.
bit would say that say x1 plus x2 must be 3, sorry, must be 1 or 0. Otherwise, the factor becomes very, very small, for example. That
Okay.
could be one example. Or in our repeater code, each factor would be that the sum of all the that each bit should be the same. And so for a very simple code like this, you would have a factor graph essentially of 2 bits, or two factors. One factor saying that the numbers have to be the same, either all zeros or all ones, and the second factor would be this. The second part of the message should be all zeros or all ones.
Okay, thanks.
Yeah, the code example is more about why this is an important problem to solve. Now, if we try to find the marginal distributions of that function, of the first variable, right, what we have to do, we have to sum over x2, x3, x4, x5. If we do this, we can sit down, write the sums for this. We very quickly, realize that actually it becomes somewhat simpler, right? So the first factor, fa, doesn't contain any of the other functions, so we can immediately pull it out of the calculation. And similarly, whatever happens inside here in the sum over x2 and x3, the sum over x4 can also be calculated separately, because x4 only comes in via the FD factor. So we can factor it out. Could in principle calculate that separately, calculate that part separately, possibly give it to different computers to calculate these things if they are very complicated, and only afterwards combine it. And that is the basic idea of the method, that because of this factor nature of the graph, you don't have to do all the sums all the time, but rather can focus on some of the subparts. Now the factor graph is I think what this paper actually sort of invented, even though
There's a quick question in the chat.
Oh, please, I can't see the chat at all. Yeah. You want to read the question?
Yeah, so it's by marginal distribution, do you mean mean marginal function?
I'm not sure what that is. But by marginal, I literally mean the sum of the function over all the variables that is not the function, the variable I'm interested in. So in this particular case, the g1 of x1, so the function of x1 is the sum over x2, x3, x4, and x5 of whatever this function is. The fact that I can that it has this structure is already an application of basic school math, that I can write it like this, but very generically it would look, oh, where was it? It would be just this, right? The sum over all
the follow-up question is like the equations that we're seeing here, the output of them, like if say we're using the large X instead of the little x, because the large X is just is like the actual domain, I think, whereas actually that's the set. But say the little x is the variables, they represent an entire domain for each of them. And the output of this function is going to be like a codomain, the codomain of G, which is like whatever it is. But that's not a distribution, because with a distribution, you'd want a likelihood associated with each of those. So what?
Yeah, this is not by itself a probabilistic problem, right? So distributions are applications of this, but this could in principle be any function, right?
Okay.
So it doesn't have to be normalized. It doesn't have to be. It is really. Yeah.
Sorry, I just meant to ask, do you use distributions and functions interchangeably in this context?
I probably shouldn't be. in this case, just think of it as functions. I'm talking purely about functions right now.
So, thanks.
So in this particular case, we have the marginal here is a function of the bigger function, but all the other variables being integrated or summed out. That's all we're talking about. It's a very, very basic problem, really. But yeah, please keep asking questions if it's not clear. One of the insights of the paper and was that this problem can actually be written as a graph. If you take this combination of factors, we realize that we have our factors, we have our variables. We can write them separately, and so each variable becomes becomes a circle. Each factor, which is a representation of the function itself, or the functional that we are defining, becomes a square. And we realize that the variables only interact ever via being in a factor together. So that means just by this very nature that the graph has to be bipartite, right? Because in order for x1 and x2 to have some sort of connection, they have to be coupled via some function. In this particular case, it would be fc, where x1 and x2 are there. So this is a very, very simple way of mapping your function to a graphical representation, which is always quite nice because people like to work with graphs, and because it sort of can highlight what is the topology of the problem that makes certain problems easier or harder. This is the first bit. Now the next bit they talk about is message passing. Essentially, we treat in this factor graph every node, be it a factor, be it the variable, as its own entity. So say the node, each node only sees whatever happens in its neighborhood. So for example, x1 would only see fa and fc, wouldn't have to know anything else. Similarly, x3, more complicated, would see fc, fd, fe. But again, because it's bipartite, each variable only sees factors, and at the same time, each factor only sees variables, which is quite handy. Message passing. So the idea is that, okay, each node has sort of, let's say it has some sort of mind of its own, and the idea is now each node could be in principle its own computer, and we want to solve the problem, say of calculating the marginals, for example, by nodes talking to each other. Now, one example, a very simple example of a message passing algorithm would be soldiers marching in a row through the forest. Imagine you are an officer of a battalion, and you want to make sure that all the soldiers are still there, but you can't see them because it's a very dense underwood. What can you do? You can actually say imagine you have the soldiers, officer at the back. You can beforehand come up with a plan that the officer could say, give the signal, I want to know right now how many people are in the row. And so each soldier could have very simple rules. If the message comes from the back, he just passes it to the front, saying we need the count. And so the signal would essentially travel from the officer through the line to the first soldier in the row. And then the second rule would be, whenever there's no one, whatever message comes from before you, take whatever is the number that is given to you and add 1 to it. So you can imagine that the first soldier doesn't see anyone in front of him, so you can turn around, say 0 plus 1 is 1, so I'm the 1. The second soldier would then add his 1 to it, and so on and so forth, until the message would have been passed back to the officer, and he would know how many people were in the row to it. And so that is an example of a very simple message passing algorithm where at any point in time, all the components only need to know what happens immediately in front or immediately after or in the immediate neighborhood, and yet you can calculate properties that sort of span the whole system. And this idea is essentially now used or tried to use to calculate the margins of functions. So nodes communicate via messages. In this particular example, a message actually is a function of the node that is receiving it. So if you are the the variable x, the messages you become that come to you are only functions of yourself. In this particular example of a binary system, you could think of it as a lookup table. It's a lookup table that tells you for each value you can have, either 0 or 1, what the function is that comes in via this particular channel.
So a message is essentially like an enumeration of the domain and the codomain, where you're like, okay, for each element in the domain, here's the element of the function in the codomain.
Yes.
Okay.
Yes.
I was wondering that.
Exactly. And in principle, if the variable itself could be more complicated, could have, say, instead of 0 and 1, could have more complicated values. It would be a bigger lookup. It could, in principle, even be a continuous function, right? Like any function of x. And we're going to talk about this in a little while when we come to Gaussians. But yeah, that's exactly it. So think of a message as a lookup table. I think that is probably the easiest way to visualize it. And now comes the two rules that we need in order to get to the margin nodes. And one rule says if you are a variable and you want to send a message to a function or factor, then you have to look at all the other factors that you don't want to send the message to right now and see, have you received their messages? And if you have received all the messages from all the other nodes around you, then you can send your message to the other function, the other factor, and that message is just the product of the other messages you have received. Right? So your variable, you send the function along, which is a product of all the other functions that you don't send to. And the other rule is that if you are a function, very similar, if you want to send a message to a variable, all you have to do.
Arvid, and for that first rule, it's because we're factorizing. Like we have this the factorization of a function is just the product of a number of other smaller functions.
Yes. Yes.
Okay.
And essentially what it comes out to is that if you apply these functions as they are defined here, you essentially get this structure back. You can sort of derive this structure by or you can derive the rules necessary to do this calculation essentially from staring at it long enough and realize this is exactly what happens. You have each factor, and say the factor fd gets information via x5, and so it has to sort of calculate what comes from the function fe via a message that has passed through. It's in my opinion very, very smart, because to come up with these rules that do this, it takes quite a bit of brain power, but it's you have to sit down with a piece of paper, but you will realize that actually the calculation that comes out of it is exactly how you have learned it in school in, I don't know, 3rd grade, and the numbers should work out. Yeah, so sorry, let me get back. So the first rule was, if I'm a variable, I want to send to any of my neighbors, I have to know what all the other neighbors have told me, and I can take the product of those and send it on. And alternatively, if I am a factor, I want to send a message to a variable. I do a very similar thing. I look at all the other variables in my neighborhood, take the messages that have come from them, also send them out, but I multiply by my own function, because I'm a function, so I have additional knowledge over all the variables that I'm not sending to. So that of course is the only way, because as we said earlier, a message that I receive is only a function of myself if I'm a variable, right? So I have to at some point sum out all the other variables, and that happens in factor, right? So the factors are ultimately the working horses, because they are doing the sums over all the variables, but because they are structured, we hope that these sums are the bare minimum necessary sums in order to solve our problems. That is quite a lot, but I hope we have some observations. So why does it work? Well, if you have a
Arvid, I have
graph,
a quick question.
yeah, please.
Can you go back to the previous slide?
Yeah, of course.
So for this second rule, I'm not. Why are you multiplying? Like my interpretation is that for these functions, like in a function node, all of like it's probably multiple functions if you're calculating different marginals with them, like depending on the direction, right? I guess that's the first question. Yeah. Okay. So in this case, I thought that the function itself takes all of the other, say you have 3 variables, 1, 2, and 3, and you want to calculate the message for 1. So you get the messages for 2 and 3, and then they're inputs to the function, no? And then the output is like some combination of them. And so I didn't. Why are you multiplying by the messages that come in?
Think of it a little bit like a base rule, right? So you have, if say your function is, you liked it, and I'm really sorry that I conflate them again. The messages that come in sort of become the prior.
Okay.
The priors for those inputs. And yeah, and because so the message that is passed from a variable to a function is just a function of the variable, so it becomes sort of the prior of that function. And so if you have the 3 functions, so x1, x2, x3, you want to know what is the effective impact of that factor on x1. You have to sum over all the states x2 and x3 can take on, times by their prior weight, which essentially is the message that has been passed from them to that function.
Okay. And then
yeah.
Okay, I'll have to think about that. Thanks.
It took me quite some time to actually go over this as well. It's not exactly. It's the infuriating bit is like the math is actually super simple if you think about it just a little bit, because it's just how products and sums work together. That these actually, these rules look probably more complicated than they actually are. That they actually work to solve the problem is kind of cool. Yeah, let's go back to our observation. So what happens if you have a graph and you have, say, a free floating variable that is only connected to one function? Because if you take the rule, you always take all the functions that are not the function you're sending to, right? But if there's only one function you're sending to, essentially this becomes a 1, right? Because there are just no other messages you have to consider when you send directly straight to the one function you depend on. Similarly for a function, if you are just a function that is by itself without and is a function of a single variable, then we can ignore the quote-unquote priors, and the only thing that really matters is just the function itself. So that's why on the boundaries the messages become very simple, what they are, and we need that, right? Because at some point we have to start somewhere from our calculation, and that essentially happens on those 3 nodes where essentially only one function or one variable is doing one thing. What was it? So the marginals, if I'm a function, actually, if I am a variable, what is the marginals? All I have to do is look at all the messages that come to me. Each one is a function of myself, right? So that the product of those, that is the marginal. And there's even a very nice other way of looking at this. Say if it's the product of all the messages that come to me, I can choose any one function, and I can say it's the message that I send to that function. The message that the function sends to me, multiplied by all the messages the other functions, the other factors send to me. And so this one function sends messages to me, the other factors also send messages to me. However, by definition of the rule, that precisely is the message that I send to that factor. So I know that if I'm a variable and I have another factor in my neighborhood, and the moment I'm able to receive a message from that factor, and I have myself sent all my messages to that factor, I know that I can calculate the marginal. Why is it a quite convenient thing? Because the marginal now depends on my neighborhood. So if I have the marginal calculated for one function, it means I already have a lot of these factors, and these factors sort of interact with my neighborhood as well. So that suggests that actually I can save a lot of the computation if I want to calculate more than one marginal of my network by essentially reusing the messages that have been already sent anyways to calculate other marginals, which is quite useful. Yeah, so in DAX, so the moment you don't have circles, it's converging, and it converges in finite time. In cyclical graphs.
Another question in the chat about the previous slide.
Yeah.
Is variable to function basically posterior probability?
It can be interpreted as that, yes. And actually, I probably should have mentioned that as well. So one of the big applications of this, and this is probably more we're going to talk about in the next couple of papers, is belief networks, where how do I update my beliefs based on different observations throughout different variables in the system, and in that particular case, that interpretation becomes correct essentially, yes. Yeah, so if I'm a variable, I essentially have to, if I want to know what is my probability distribution, I have to know what are essentially the priors that come from my immediate neighborhood, yes. Again, this is an interpretation. This is arguably more generic because it does not require your functions to be normalized or anything, which is, yeah, quite handy. And I think we have somewhere so how would it actually work in practice, right? So I'm a node. So each neighbor, or I am done as a node when I've received a message from all of my neighbors, and if I have sent a message to each of my neighbors. So I know when I'm not done, and I know when I'm done. That is already quite useful. And I can only send a message if I have received all the other messages that are necessary, right? That's just the basic rules we discussed. If I want to send a message as a variable to a factor, I have to know all the messages that came from the other factors first. Otherwise, I can't send it. Well, end nodes are the ones that start going on right away, just because they don't have any dependencies. That's why they can just send immediately. And yeah, and all the nodes could in principle work at the same time, right? So you could imagine to sync the system, or even asynchronously, that the moment a function receives all the necessary messages, it calculates all the messages it can send. And this way, there's no need for all the nodes to be ordered in some way, or that they have to talk to each other, rather than they just do whatever they do at the time they can do it. And if you imagine what is the worst case scenario in order to get a marginal principle, you have to, at some point, you have to send a message to the factor, and we discussed that we only know the full marginal once the message has come back. So that means if there's, say, only one factor, the worst case scenario is that the message I send out has to travel essentially to any other node in my graph and has to come back. So there's also the maximum size the message has to travel, right? So I know that the size of my graph limits essentially how long it takes for my marginals to be calculated, and that is essentially twice the diameter of the graph. So this is now finally an actual example of the function we talked about. So we recognize our 5 factors of A, Fb, Fc, Fd, and Fe, and our 5 variables, x1, x2, x3, x4, x5. And the messages that are being passed are numbered. So all the messages with a 1 are sent essentially at the same time, right? And we see it's the nodes that are on the very outside that have no direct dependencies. So the factor of A, the factor of B, because they only depend on one variable, they can immediately send their input. Same is true for the variables x4 and x5, which only depend on one factor each. They can also immediately send their messages.
Arvid,
So,
when
yeah.
I saw this, it was a bit confusing to me because I thought that I don't understand how you can have like what I'll call boundary nodes that are factors, because I thought that like you'd have to have some kind of variable that sends a message to a factor before a factor can be activated.
It depends on the number of dependents, really, whether right, because factor fa, for example, is a boundary because it only depends on x1.
Mm-hmm.
Now x1 also works in the factor fc, but yeah, but fa does not need to, in order for fa to know what impact it has on others, it only needs, it doesn't need to know anything else because fa doesn't depend on anything else. So that's why it works. It's more like when is a node, or when is a variable a boundary, and that is when the variable itself only appears in one factor. So that is almost like a global property, right? So imagine if, in order for me to know whether I'm a node, I have to know anything about all the other factors just because they are the ones that sort of glue the system together.
I think I get it. So if you have like a factor that's a boundary node, that means that it essentially doesn't affect any of the other factors because it's got like the input variables to it are like
Just the
you
one
can
function.
create a line between them and that. So you just need to know the input variables for the other factors. You don't need to know the actual factor.
Exactly. And from the graph, it also becomes clear where you have like sort of bottlenecks, right? So any function that has to talk, like if I know x3, I don't, if I know the message that comes from variable 3, I don't have to know about x4 and x5 just because their impact on, say, x1 or x2 is already integrated out because there's no other way for them to like pass information around to x1 except by going through x3. And the cool thing is, right, so imagine in the very worst case, a particular message would have to travel. So step 1, step 2, step 3, step 4, step 5. In the very worst case, it could be that the message has to travel back as well in a similar way. But in this particular case, because the structure of the graph has this sort of bottleneck, we don't actually have to wait for the message to really come back, because all we need to know at x1, for example, or at fc coming from f3 can already be calculated at the same time I'm still calculating stuff of x1, right? So it actually saves time because the messages can run in parallel, because they only calculate whatever they need in order to proceed, which is quite nice. And so we see that in this particular case, say if I want to know, say what is f1, right? So say I want to calculate the margin of f1. In the very first instance, I can't do anything because I, as x1, want to send something to fa or fc. So in order to send something to fa or fc, I have to know the message of the other, but at the very beginning, I don't have it. However, after the first time step, fa sent me something. So now x1 can look around. Okay, the only other node is fc. I have all the information necessary, so I can send my message to fc, which is essentially, I think it is f1 of x, right? Because it just is the product of all the incoming messages, and the incoming message is fa of x1. And similar fc, now it sees it got the message from x1, but because they're all running in parallel, at the same time also got the message of x2. So now fc knows it has enough information to send its message to x3. And now x3 can send the messages then on so forth. But the messages that have been sent from x3 to, say, to the x4 direction are not necessary for fa anymore. It actually can immediately receive the message coming from x3 via its path of the graph. And so we essentially can run everything in 5 steps, even though the maximum distance between 2 nodes would be 10. So we do save time, which is quite nice. Was that remotely clear? No.
No, yeah, that made sense to me.
Okay. So what have we used actually in order to come up with the rules, right? So if you go back to the very beginning, right, we realized that in order to calculate marginals like this, we actually, the only thing we made use of is the fact that we can use this distributive law, that common factors can be factored out. And so, common factors have common graphs. So they can move out. So that is actually all that was used to derive these rules of this message sending. And it turns out that there are actually other combinations that have similar rules, and perhaps most importantly is the product and the maximum. So if I have non-negative functions, as it's the case for probabilities, for example, then actually the maximum also obeys this rule that common factors can be factored out. So now the beautiful thing is that the whole mechanism of how message passing works to calculate marginals can be also applied to calculate the sets of, or the elements of the domain that maximize a function. And that, of course, is super valuable. If you think back to the error codes, that is exactly the problem that is very, very important. What is the combination of inputs that maximizes my function? So yeah, that was just what I said. It's very practical. It's used. It's very closely related to what's called the dynamic coding, I think. Is it? I forgot the word. And the problem, and of course, in the practical application, is that the products of small numbers become very, very small. So actually, what is often being done is that the messages are turned into logarithms. So rather than having, if I want to send a message to a factor, rather than taking the product of small numbers, I actually just take the sum of the exponents. The only thing that makes it a bit more complicated is that the summing becomes more difficult, but this can be sort of solved with lookup tables, where because of the exponent doesn't move that much, then the sums can be easily looked up. And that's why the max product algorithm is also often called the max sum algorithm, because products and sums are sort of related with the exponentiation rules. What is an example of a continuous system that follows a similar set of rules is the Kalman filter. Essentially, what is the problem? We have a variable that, say, x in this particular case, and x could evolve over time, and we make measurements of x. The measurement is called y. The measurement y is a function of x, so a linear function, but each measurement is also noisy. So we have the problem, we have a variable, we don't know x, we get incomplete measurements of that variable x, and that variable x is also moving in time via some factor. It can be generalized to the matrices as well. And we want to know at any point in time what is the distribution of x we have. We can what was our belief state essentially about x. So we have inputs there. There's the important bit is that the noise here is Gaussian, and we say that at the beginning x is 0. So if you know where it starts out with, because it's a Gaussian problem, it actually turns out that the problem becomes algebraic, so that the messages, I'm going to say in a moment, the messages that actually passed could be functions, but because these functions are all Gaussians, and Gaussians are completely described by their parameters, all it needs actually is to pass these parameters. So there are simple numbers again. So if we write this out in a graph, we have our variable xj. That is essentially how we ask what is the distribution of xj at the point in time, or x at the point in time j. all we need to know is what is our prior essentially going in from how xj minus 1 looked like, and what is the measurement we have right now of xj, and we can calculate the distribution of that. In the next step, the information we have gathered, we can send to the next node, which would be what is the state of x in the next time step, and it would continue like that. So that is a continuous application of the same algorithm, essentially, the message passing algorithm. Here it only goes in one direction though. And because it's Gaussian, it's slightly different. It works fine in practice because all the products and summing becomes essentially products of Gaussians or convolutions of Gaussians, and these essentially are translated into algebraic operations. And if we plug this in, we get actually these equations for how the mean of the variable we're interested in, so xj, would update because of these message passing rules. Essentially, it's the prior mean plus the difference of the observation to the expected observation times some factor, and that factor again follows directly from the messages or message algorithm that we calculate are called the Kalman gain, and a nice factor. So this only goes in one direction. A nice application or a nice insight is that if we say a and c are equal 1, so the variable that we're trying to measure xj does not move in time, so it's just a simple function, a simple variable. It doesn't change. We only have different measurements of it, and the measurement itself is that variable. We see that we can update our expectation of that value by this factor that is essentially our uncertainty about that factor divided by the sum of the uncertainty and d. And if you remember what d was the 3 factor to the noise term. So it becomes a sort of signal to noise ratio. So this is then, these Kalman equations follow directly from the message passing and tell us if we have different variables that we're trying to measure, one variable we try to measure in different measurements, that each measurement should be weighted by how noisy that measurement is. And that is, of course, super useful in also a lot of applications. If we want to update our knowledge about something, for example, ratings about the player, based on what we've seen from that player, for example. And this Kalman filter we talked about only works in one direction, meaning that we don't update our belief state because of future events, only of past events, but that doesn't have to be the case. We could very well think of a case where, say 2 players play with each other, and then the next week someone else plays. One of the 2 plays against a player we know very, very well. We could imagine that knowledge actually should probably also go back into how we see that player in the first place. So there is room to making Kalman solutions that also go backward in time. Yeah, so that is one of the probably most direct applications of the basic message passing algorithm. So that sort of sums it up. God, I think I'm really rambling here, but so the idea is that we have an algorithm that is a very simple set of rules that can calculate complicated properties of the whole graph, essentially, and of all the functions. It's very effective because a lot of the calculations can happen in parallel, and the factors that are the messages that are being calculated in the meantime can be reused to calculate all the other marginals as well. So that makes it very efficient. It has tons of applications in the real world, be it from the error decoding, be it from Kalman filters, or yeah, it works directly only on the directed acyclic graphs. However, there are also rules that do work in some cases for cyclical graphs. They are, for example, used in turbo codes, which are, I think, the state of the art in encoding and decoding error-free messages or noisy messages. And it converges generally fast because of this very structured nature of the problem. Now, the issue, or this particular case, was mostly about discrete messages that are being passed. In reality, often the functions we were talking about are not directly Gaussian, and or they are not discrete. And how one could solve these systems when they have more complicated messages that have to be treated in an approximate manner, that becomes the subject of the next paper I'm going to present hopefully next week. Yes, that's it. Thank you very much.
Thanks,
Any
Arvid.
more? Any questions?
Is besides max, min, sum, how about max, min, product?
Max min product. What's that?
Like instead of because it's sum product is like two operations that you apply. Can you apply like max or min with product instead of max or min with sum, and this stuff falls out as well?
So I would think that min product should work, right? Because min product also has this distribution rule, right? That A times B, the minimum of A times B or A times C is the minimum of A times is A times the minimum of B and C, provided of course they are all positive. So yes, that would immediately be applicable. It's just that in practice we often care more about the maximum likelihood than the minimum likelihood. But I think it's a fair question. There might be applications to that as well. Yeah.
And so these factor graphs we've been looking at, if you're calculating a single marginal, they're directed. But if you're calculating like all the marginals, then they're not directed, right?
How do you mean? The graph itself doesn't change its form, right? The graph itself is only determined by the function you're calculating. So whether your graph is a DAG or not should not depend on that, essentially.
Okay.
Because
Well,
it's essentially,
I was just asking. Yeah, go ahead.
Because it's a function of the topology of your graph, essentially. And so all the properties of how long it takes to to have enough knowledge for any node to know how its margin should look only depends on the topology, but not, say, if you rotate that graph around, or if you the nodes are not fundamentally ordered in a graph.
Okay. Are there computational constraints? Like if variables have enough of a large enough domain, does this become intractable still?
Yeah, so that is a bit the issue. Talking next week about what happens if the messages that are being passed are actually proper functions of continuous variables, right? And especially functions are not just mere Gaussians, as in the Kalman case, where it's actually nice and solvable because it's essentially an algebraic system, but rather if can talk about say what happens if a measurement could be a measurement, but there's a small chance that the measurement is actually just pure noise, but you don't know it. All you see is the outcome of the measurement, and that's the system. There are approximations that sort of deal with that, and that if not handled correctly, that becomes essentially infeasible, right? So the moment you have like generic integrations or so, things can get very difficult, and then the things the message you pass should still be very, very, very simple. Now, I think Microsoft actually built a tool, what's it called, inference.net, I think, or something like that, based on these rules alone, which essentially has, I think, where each factor and each variable is specified in these rules and by its update rules, and it sort of becomes a generic solver for these graph problems, and I think it is used in practice, which is then I think what the third paper is going to be about, the truth score, which is one of the I think most widely used large-scale Bayesian inference algorithms, really. Any other questions?
Someone raised their hand, but
Yeah, I did. Thanks. Sorry, I just had a question about going back to the marginal function, because it seems very reminiscent of Bayesian approach and of the stereo function. But what's the difference there?
Well, a Bayesian approach is a bit more is a bit more restrictive, right? Because in the Bayesian approach, your functions have to be positive, right? So your belief states are not negative, whereas this generic graphs would in principle work with negative functions as well. Because because the marginal can be negative, whereas your marginal belief state gotta be always positive, unless you have some really weird law of probability, which does exist, but it's they exist. I think it's in the Jane's book. If you reformulate probability theory to be, I think, absolute confidence being mapped to infinity and absolute like a zero belief state being mapped to minus infinity, that would in principle work, and then you would probably need these rules rather than the simple Bayesian belief networks as we are more used to them, really. But at the end of the day, it's a cultural issue rather than a fundamental issue.
Okay, thanks.
Anything else? I think we are also time. So
yeah, thank you, Arvid, for this presentation. As always, very good and very informative. And well, I guess if you have time next week, we'll do the next paper. If not, then one of us will present. Just let us know on like Monday or something.
Yeah, it's planned. It's just that sometimes very short notice things can come in. So that's
okay, yeah, like there's an outage.
To have something in case just if boss says I can't do it for whatever reason. So yeah.
Yeah, sure. So I'll put it in that you're presenting next week, and if it has something last minute, then I'll just have a paper ready. But anyway, thanks everyone for coming, and thank you, Arvid, again, and have a nice weekend.
Bye-bye.